So let's see what our last two examples look like when we graph them. So I'm going to plot the function sine x. Let's go x from negative 5 pi to 5 pi. And let's plot between negative 5 and 5. So there's the graph of sine x, familiar graph. In the last videos, we found the Taylor polynomial for sine x at x equals 0. So let's see what that would look like. I'm going to start maybe with n equals 1. And I'm going to write down my Taylor polynomial. So my Taylor polynomial was negative 1 to the k, x to the 2k plus 1 power. Remember from our derivation that only the odd powers of x really survive in the Taylor polynomial. And I'm going to add these terms up from k going from 0 to n. So my degree 3 Taylor polynomial is here. Let's plot that alongside sine x. So at x equals 0, remember 0 was where we're trying to approximate the function. I get a very nice picture. The graph here, the gold graph, that's my degree 3 polynomial, matches the function sine x near 0 very well. Let's increase n. Let's do n equals 2. That'll be my degree 5 Taylor polynomial. So let's plot that. Let's get this again. There's the degree 5 polynomial. The window on which my approximation is good is enlarged. My approximation gets a little bit better around 0. Let's try a bigger value of n. Let's try n equals 5. I guess this gives me the degree 11 Taylor polynomial. So I'll plot that. Oh, wow, look at that. Look at that. Very nice. Let's even go bigger. Let's do n equals 20. This will be my degree 41 Taylor polynomial. So let me put that in. Got my degree 41 Taylor polynomial. Oh, look at that. Look at that. That is so nice. Maybe I should plot this from a larger window. Let's go from negative 10 to 10. Oh my gosh, look at this. Look at this. The Taylor polynomial perfectly matches the graph of sine x on this window. If I increased n, this was just n equals 20. That gave me the degree 41 Taylor polynomial. If I increase that, the function would be even better of an approximation. The window around 0 that my approximation is good would get larger. Of course, the approximation gets horrible if you try to stick in 20. So at x equals 20, the graph of sine x, the blue graph, is very far away from the graph of my polynomial. Okay, so that was the example with sine x, but I'd also like to show you what happens with the function 1 over x. We also found the Taylor polynomial for this. So let's plot 1 over x going from negative 1 to 5. Let's plot from negative 1 to 5. So here's the graph of 1 over x. The graph of 1 over, actually, let me plot from negative 1 to 8. So here's the graph of 1 over x. We also found the Taylor polynomials for 1 over x, centered at x equals 3. So our formula for that was the sum, negative 1 to the k, x, I think we had a 3 here, 3 to the negative k plus 1 power, 3 to the negative k plus 1 power. And all that was times x minus 3 to the k. So here is my first Taylor, x minus 3 to the k. So here's my first Taylor polynomial. Let's plot this and my function. So remember, I'm centering everything at 3 for this example. So my tangent line, that's my degree 1 Taylor polynomial, is tangent at x equals 3. Let's increase n equals 2. I get my tangent parabola. I get a little bit of a better curve around x equals 3. Let's go bigger. Let's go n equals 5. So I get my degree 5 Taylor polynomial. It should match the graph of the function very well around 3. And you can see it does. Around 3, I get a really nice curve here that's matching the graph of the function. But something strange is going to happen in this example that did not happen in the last example. When I do 10, try to see what's going to happen. This one's a little bit different for a subtle reason. So look at what happens when I plug in 10. Again, around 3, my picture is really great. But around 6 or 7, you know, the gold polynomial and my blue function really don't match. They don't match at all. Very different. Let's increase to n equals 30. N equals 30. So I have the degree 30 Taylor polynomial. Let's plot that. This will really be dramatic. So this is kind of odd, actually. Again, around 3, my approximation, great, wonderful. It's almost perfect. But I guess at around 6, my approximation starts to get horrible. Around here on this side of the picture, things are going great. But over here, things are going bad. There's a reason for that. That's part of our course. We're going to talk about it. Let's increase this even more. Let's try 50. Let's try 50. Oh, wow. Okay. So let's put that in and plot. Yes. Increasing n makes my approximation around 3 better, but it does not make my approximation better after 6. So there's some kind of cutoff at 6. There's something happening at 6 that makes my approximation break down. And that will be the discussion we'll have in future courses. All right, see you next time.